initially I have given you a lot of examples where I told you that when we are talking about frames of reference and we want something to move at a very fast speed, a rocket is a good example, which escapes the surface of the Earth. Then the Earth may be considered to be a reference, frame of reference, and if someone is sitting in the rocket, he's in another frame of reference. Okay, so this idea is very important, and this is why we told this initially. So he or she may be an astronaut and traveling to outer space. Okay, so if that happens, that person on board will actually experience something different from something which we experience on Earth, right? So maybe the question would be like this: a rocket with initial condition. This is not taken from any book, okay? So, but similar question does exist. With initial condition t is equal to 0. So, time 0, matlab the launch has not been done. Okay, and when the launch was done, the velocity was 0.6 c. So it's one order less than the speed of light because we have a point here, but then this is the velocity which is given, and this is actually launched. So we are basically trying to launch it from Earth. So this is launched from Earth. So see, be it in any subject, okay, physics, chemistry, maths, any engineering branch that you are in, if you are solving a numerical problem, it's very important that you understand the question first, and then only you target how you actually are going to approach with the answer. Okay, so basically we have a rocket which is being launched, and there are two watches. Okay, there are two watches, one is on the Earth and the other one is on the rocket. Okay, and we are actually trying to measure time. I might say that we have still not done time dilation. Will this problem lie in time dilation? It will, but right now we are going to use only Lorentz transformation. Okay, so the question is, a watch measure 1 hour which is placed on the rocket, which is on the rocket. So we have a watch which is on the rocket, and the rocket is moving, and the time that it measures, that means the watch on the rocket, is nothing but 1 hour. So that means if you are on Earth and you are also measuring that time, you are going to measure something different. Okay, that is the idea of time dilation. Okay, so what happens after 1 hour? After that 1 hour has passed on the watch which was on the rocket, this is a very interesting problem. Okay, it sends a pulse. So that means maybe it sends a flash of bulb, a flash of light, ready. So it sends a pulse signal. It may be any kind of electromagnetic wave, maybe, right? So signal, it sends a pulse signal, okay, to Earth. So it basically has a pulse signal which is sent to the Earth, and we have a detector here which detects that pulse signal. Question is, I think question is easy now to understand. What is the time measured on Earth frame? Measured on Earth frame. Earth frame. So, if I say that a rocket has gone into space, and in that rocket the time is 1 hour, that means from Earth, if I measure, the time will be longer, because that's called time dilation. And then the pulse starts, that hour has passed, and then so maybe this is your Earth, which is nothing but the S frame, and then this is your rocket, right, which is the S prime frame. So it takes 1 hour reaching from here to here, from here to there. Okay, so let me write it down as X hour, because it's 1 hour of the rocket, but from Earth to space, that 1 hour, how much we will measure it, we are going to do it, so that will be different, maybe it's X hour. And then what happens, a pulse signal is sent back. So that signal will also take some time to travel from that rocket to the Earth. Okay, if we add both of them, we are going to get what is the time measured on Earth frame. Okay, when the pulse signal is actually calculated. Okay, so how we are going to do it? Okay, we are basically going to consider two frames of reference, and the first frame is the rocket frame. Okay, and the rocket frame is nothing but the S prime frame, right? So we are just considering it to be the S prime frame, and we are considering an event here. And what is that event? Event is the signal that we are sending. Okay, so signal sent. So we have the signal that is getting sent, and that is actually the the event that we are considering. So if we are in the S frame, okay, I hope we understand this very clearly, because we have the watch on the rocket. Please understand this. We have the watch on the rocket. That means the time is equal to nothing but 1 hour. Okay. And then what is my X prime? X prime is equal to 0 because there is no change in X dimension because we are measuring that inside the rocket. So it's inside the rocket. This will help us to analyze this better. So now what we do is we actually are going to measure what is the time from the earth. So for doing that, we already have a relation. X is equal to X prime plus Vt prime. You remember the reverse transformation or the inverse transformation. The relation originally was X prime is equal to X minus Vt. If we are changing the system, we are measuring X in terms of X prime. In place of minus v, it will be plus v, right? And the denominator doesn't change because there is a square term. So this is 1 minus v square by c square. So this is the Lorentz transformation that we have already seen, okay? And then we also have the relation for time, which is nothing but t is equal to t prime plus vx prime by c square. Okay, you can check that. We have already written this in your notes. It should be there. 1 minus v square divided by c square, right? Now what we have is, it's already given that v is equal to 0.6 c. Okay, so that means we can actually measure it here. Okay, it's very simple. T prime, okay, see, this actually clearly explains that which time we are measuring. T prime is nothing but the time in the rocket, so that is actually 1 hour, which is already provided, plus X prime is 0 because we are measuring it inside the rocket, so this becomes 0, very simple, and we have got it as divided by 1 minus v square by c square. So v square means 0.6 c whole square divided by c square, right? So if you do this calculation and check, okay, this would be nothing but 1.25 hours. We have it as 1.25 hours. So that means the time that you measure from the earth for the rocket to reach that position, inside the rocket it is 1 hour, but if you have a watch on earth, that will actually measure 1.25 hours. That is the entire idea of time dilation. Okay, so you have to remember or understand this. This is very important. So that means the time that we are talking about, therefore time. So when you write down in your exam also, you should be very clear about what you're writing as per Earth's frame. Okay, so we can consider this to be the S frame, right? Earth's frame is equal to 1.25 hours. Okay, now the question is, the signal has to reach back to the earth. Okay, so for that we should know what is the distance, okay, and then only we can measure the time, right? So the signal, it's sent. Signal is sent. The question is, how much time does it take? I'm just writing this down so that it's very clear to you the idea. Time it requires to reach the earth. Yeah, requires to.
Color person.
Someone's mic is on. How much time is required? How much time is required for signal to reach earth?
वो तो तू देखना कलर परसों फ्री है कि नहीं है
कल परसों क्लास नहीं है ना, सैटरडे संडे फ्री होंगे. या someone's mic is on. कौन बोल रहा है?
ठीक है देखते हैं
disadvantage. Aditya Chawla. Aditya. Aditya, are you there? Okay. So when I'm taking the class, at least be careful and just make sure you don't switch on your mic, because क्लास करना भी ज़रूरी है और समझना भी ज़रूरी है. तो आप लोग थोड़ा ध्यान दो, बाद में फिर बोलोगे कि समझ नहीं आया, then it will be difficult, right? Okay, signal sent. So the question is, or what we want to analyze here is how much time is basically required for the signal to reach Earth. Okay, this is something which is important. So we are going to measure that. So if we want to actually measure that, we actually want to know what is the time. So we know time is equal to distance by speed. Distance divided by speed. And we have to measure what is the distance, right? So we don't know what is the distance. So what I'm going to do is I'm going to find out the distance here. We are talking about a light pulse. That means the speed is c, we already know. So distance is equal to velocity, which is already mentioned to be 0.6 c. Okay, so that means I want to measure at what distance, you know, the spaceship is, so that I can measure what is the time that the pulse takes to reach from here to here. So I want to measure what is the distance the spaceship is. So I know it travels with a velocity 0.6 e into time. So as per the Earth's frame, the time that we are measuring is 1.25 hour. So that means we have it as 0.75, okay, c hour. C hour means, you know, you can just convert it. C, you know, is meter per second square. You can convert it into hours and then cancel it out. You'll get the answer in meters. Okay, so I'll just keep it as c hour, no problem. That is also a unit of distance, right? I'm just not converting it. If I multiply these two and take this c into fundamental units, you're going to get the measure unit of distance. So this is 0.75 c hour. That's the distance, right? Therefore, time that the pulse takes to reach Earth from the spaceship is distance, which is 0.75 c hour. So it becomes simple.
Sir,
Divided by, yeah,
sir,
speed.
how distance is coming in hours?
Yeah, I'm telling you that. I'm going to explain that to you. Okay? Okay. This is not hour. The unit is actually c hour. C hour. With c matlab kya hai? C matlab speed of light. That means this is nothing but meter per second square. Correct? Unit hai ye. And this is basically, you know, hour. Right? Sorry, meter per second. Speed, hai na? Meter per second. Now, what you do is you can convert this meter per second into hour, right? How do you convert seconds to hour? You can just take meter per second and divide it by 3600, right? Into hour, right? So whatever you have here is basically in hours. So you can just cancel this out. Then the answer is meter. So unit of meter distance is meter, right? Is it clear now? Why it is?
Yes, sir.
Yes. So when you multiply hour with c, you are going to get the unit of distance. Here I'm just writing this down and keeping it as c hour, because when I measure time, I have to write down distance, which is 0.75 c hour divided by speed. Speed, that means we are having a light pulse which is coming down. That means it is traveling at the speed of c. That means this c and this c will get cancelled out. I will get the answer of time. Time is 0.75 hour. I just did not convert it because there is no need. I'm going to find out time. This C and that C will actually just get cancelled out. So anyway, I'm going to get the answer to be hour. So that means the rocket has reached this particular point as per the Earth frame in 1.25 hour. And then it sends a signal, and the signal comes down and it takes a time 0.75 hour. That means the total time that is required is nothing but 0.25 plus 0.75 hour. So this is just a pictorial idea, or I think it's clear. But then this is the answer. Okay. So therefore we can just say, if we just want to, you know, conclude, therefore as per Earth's frame, So you keep asking questions, okay? It's good that you're asking. You have any doubts, you have to ask then and there. It's very important, so that हम लोग सबका clear हो जाए, ठीक है? Sometimes your question might be very, complicated, but still you ask. If I'm not able to answer, I'll just make sure that I find out an answer and answer it to you in the next class, ठीक है? But सवाल पूछना बहुत जरूरी है. No question is a
Sir?
stupid question. Every question is important. Yeah, tell me. Signal
Sir,
starts.
when we change meter per second into meter per hour, then you have to multiply or divide by
Okay.
360.
Let's say 10 seconds, right?
Yes, sir.
10 seconds is equal to how much hour? So in general, when we say, let's say 1 hour, right?
Yes, sir.
1 hour is equal to 60 seconds into 60 minutes. Is this one clear?
Yes, sir.
So this is 60 into 60. That means this is 60 into 60 seconds, correct?
Yes, sir.
So if you look into the unitary method, that means 1 hour is equal to 3600 seconds. मतलब सही है?
Yes.
मतलब अगर मैं unitary method use करूँ, that means I have to divide both sides by 3600. That means if I divide this side, this would be 1 divided by 3600 hour is equal to 1 second. Is this one clear now?
Yes, sir.
Right. So जितना भी second होगा, suppose मेरे को 10 second हो रहा है, then this will be nothing but divided by 3600, because 1 second is equal to 1 divided by 3600. That means 10 second is equal to 10 into 1 divided by 3600. Is it clear? So this will
Yes,
be
sir.
hour. So whenever you take seconds, you divide it by 3600, it will become hour. So मतलब seconds divided by 3600 is hour. You cancel that hour and hour, you get the unit to be in distance. Okay? So unitary method. So eventually you will see, unitary method is such a powerful tool. Let me tell you, we all get confused. Okay, even I get confused at this time. Okay, after teaching for so many years, I still get confused. The best way to understand this is use the unitary method, because you are going to use it every now and then in your engineering branch. कोई भी branch में हम लोग use करेंगे उसको, ठीक है? Very important. So as per Arch frame, this signal starts. Okay, आप लोग थोड़ा खुल रहे हो question पूछने के लिए, is very good. Okay, तो आप लोग question पूछते रहो, don't worry. We'll try to find out all the answers. This signal basically starts, okay, traveling, okay, and reaches Earth after. So, even if you don't explain this, this is fine. I'm just explaining it for your own reference. 1.25 plus 0.75, which is equal to 2 hours. Okay. So after the launch, maybe after this, after launch. So this is important. So ये question देखने में बहुत complicated लगता है, but if you understand the logic behind, I think you will get the answer. Okay, so this is actually a complicated question. If you understand it, this is important. So what I will suggest is all of you write down this answer. If you have not written it, maybe I'll just keep it on this screen. Take a screenshot. जल्दी जल्दी एक screenshot ले लो. उसके बाद answer वाले में रखेंगे, उसका भी screenshot लो, and then you just check it once. You do it on your own and you compare it with this. Okay. So these kind of questions are something which I might also ask. So, if you understand this question, any other question will be something similar. We will see eventually that there is a very simple formula for time dilation, where we don't need to use really Lorentz transformation and we can get that answer. Okay, that is also possible, but we are going to do that later. Okay, we'll probably start with that topic today. We don't know if we can finish it or not, okay? But this is an important problem. So if you've taken a screenshot, you can take a screenshot of this now. Okay, maybe. ठीक है, तो ये वाला screenshot भी ले लोगे तो हो जाएगा, और उसके बाद the next one. Okay, नीचे में तो आंसर दिया हुआ है. So up to this point you already know it. Okay, that's just the sentence at the bottom. So it is 0.75 plus the 1.25. So that's 2 hours in total. ठीक है, so आप लोग ये जरा देख लो. ये वाला तो चलो नोट है. This is material. So this is actually a question which will carry as good as 3 to 4 marks, because इसको तो समझ के करना पड़ेगा. So these kind of sums are there, and these kind of sums will actually help you to understand the importance of relativity, the importance of Lorentz transformation, and so on. Okay, imagine, okay, एक hypothetical situation सोचते हैं. the speed of this rocket is not 0.6 c, okay, 0.6 c. It may be much less. It may be, let's say, 100 meter per second square, something like that. If you put that value, you will see that this thing becomes very irrelevant. It is very close to 1. And then your answer will change. It won't be 1.25 hours, okay? It will be very close to 1 hour. So this is actually something which is happening mathematically, but the understanding is very clear. If the speed is very high, this increases. If the speed is low, this will be very close to 1 hour, which will be almost like the same watch as that space placed in the rocket. So now imagine if I'm asking you a question where I replace this rocket with a train, okay? So आप लोगों को question कैसे आ सकते हैं? I can replace this rocket with train. अभी ट्रेन का स्पीड थोड़ी इतना होगा. It's not like, you know, मैट्रिक्स का ट्रेन थोड़ी है. So the train speed would be maybe, let's say, it's one of the fastest trains, okay? Let me put 300 km per hour, maybe. So your homework may be this. Use the same formula, use the same technique, okay? This can be taken as an assignment, okay? Consider this as an assignment. Rocket is replaced with train, and then this is this. It is not launched, okay? Obviously not launched, is moving, let's say, moving on Earth, right? And then which is on the train. Now this is on the train. The watch is on the train now. After 1 hour, it sends, you know, maybe a pulse signal to starting station. Maybe it's a straight train. We are imagining a starting station. What is the time measured on the starting station? Same thing, okay? The idea is the same. So you see how I twisted the question, but idea is the same. So if I give you this question in exam, you should be able to answer it, because it's the same example as rocket. The only thing is that the velocity is different. The concept remains the same. Nothing changes. Here it was just going from, you know, moving on the y-axis. Here we're just talking about the x-axis. So we have got the starting station here. Maybe this is the S frame. We have got the train here, which is nothing but, you know, the S prime frame. So there is a watch here, which is, let's say, T dash, measuring time, and here it is T. That's it. The problem is same. Nothing changes. But if I give you this question, you might say, sir, ये out of syllabus हो गया. It's not, right? It's the same question. The only thing is that there is a difference in velocity. Now, when we put this value of 300 km per hour here, okay, imagine now, यहाँ पे I think a concept will be clear even more. So here it's 300 km per hour. So the speed is, distance is not 0.6 c, because the speed is 300 km per hour. So it is 300 km per hour into 1.25 hour. Hour will get cancelled. It will be just in kilometers. Okay, so whatever answer you'll get, you'll be in kilometers. Okay, so you do it, use your basic logic, basic idea, you'll be able to solve it. Take a screenshot of this also if you have not written it. If you have written it, it's fine. Write down the values. Okay. Usually 300 km per hour is the maximum train speed, okay, if you consider it in India. Otherwise it can go up to 500, 600 if you're talking about those bullet trains or G trains, okay. So we can take this. So ये एक example है which is important. Now the question is, we actually talked about Lorentz transformation. Is there is a special case where we can say that if the speed is low, this Lorentz transformation will tend to Galilean transformation. So this is important, okay. So what I'm going to tell you now is something which is very logical, but I think you'll understand this, okay. This you can consider it to be a after note, but then this is an important part of the syllabus also, okay. This Lorentz transformation that we talked about, in Lorentz transformation we were actually only talking about speed of light, okay, something which is moving comparable to the speed of light. So this Lorentz transformation, which actually will tend to Galilean transformation, at low velocity, because Galilean transformation is only valid at low velocity. So the Lorentz transformation will tend to Galilean transformation at low velocity. Okay, so this is what I wanted to explain. Okay, want to explain because here what happens is Lorentz transformation or Galilean transformations are connected. It's not that we have Lorentz transformation means Galilean transformation is wrong. No, that's not true. Okay, so in general, when we talk about Galilean transformation, we know we have seen it several times. X prime is equal to x minus vt. Okay, but when we talk about the Lorentz transformation, we know x prime is equal to x minus vt divided by root over 1 minus v square by c square. So this will tend to this. Yeah,
Sir, this low velocity is with respect to Earth or what?
anything. Okay, anything. Good question. Anything. So let's say, as we have talked about it in so many examples, suppose there is a bus and your friend is inside the bus and you are here on earth. Maybe you are standing on the ground and your friend is here, and this bus is moving at a speed of, let's say, 100 kilometer per hour. What's fast there? So this case is low velocity. Your friend is moving at a lower speed. That means the distance that is measured on this particular frame of reference with respect to this frame of reference will be given by this particular relation. Okay, you can measure your friend's distance from the bus or the bus's distance from your friend. Okay, you can do both, and it will be actually dependent on this velocity. So we can actually measure it using this formula. But imagine it's a hypothetical situation, some sci-fi movie where the bus is moving at a speed of 0.6 c. That means the velocity is 0.6 times the speed of light. That means it is 0.6 into 3 into 10 to the power 8 meter per second. If this situation exists, which is not true, but hypothetically, if that is there, then the formula would be this and not this. This is what is meant by frames of reference. If you go to the previous problem and check here, we see that it's actually 0.6 c. So if it is 0.6 c, that means we are using this formula, which is here. But if I'm mentioning about train which is 300 km per hour, even if you use this formula, you are going to get an answer which will be similar to a formula which we use like this, Galilean transformation. So यहाँ पे I have told you कि you use this formula to find out the answer, but you can also use the formula x is equal to x prime plus vt, and you will see that the answer with this and the answer with this both are similar or very close to each other. Okay, that clearly explains that if the speed is low, Lorentz transformation becomes insignificant, and that is very important. Now the question is, what exactly do I mean by low velocity? So if I say something like this is not low velocity, this is very high velocity, because if you talk about the order here, 0.6 into 3, okay, that means you can take it to be 6 into 3, which is 18, okay, into, और यहाँ पे तो divide by 10 कर दिया, तो ये still with one order will get cancelled. This is 10 to the power 7 meter per second. So I can take it to be 1.8 into 10 to the power 8 meter per second. So see, in maths, physics, okay, engineering, wherever you are using numbers, if the order is same, this value is very insignificant. Okay, this doesn't make much of a difference if the order is there same. Okay, if the order is, especially in higher cases, okay, mathematically that's true. So that means this is very much comparable to the speed of light. So in that case, we cannot use this formula. Okay, this formula is not valid. We have to use this formula. What is the reason for that? I think we have explained it in Lorentz transformation. So I will upload the lecture tomorrow, so you can again check that again in case you have missed the class or you just forgot. Okay, so I think you can check that. So Lorentz transformation, I have to clearly mention why speed of light is important to understand a system. Now let's imagine that it it's low velocity. Low velocity का मतलब ये होता है कि the velocity that we are considering is very small compared to the speed of light. So what does it mean? In this particular case, we can do some modification. First thing, x prime is equal to x minus vt. There is no c involved here, so I don't need to do any kind of comparison. Divided by root over, see, this is 1 minus v square. And what is the value of v? V is very small compared to c. Okay, so that means it's very less compared to c divided by c square. It's very less. So I hope you understand this, that if you take a very low value, let's say 0.0001 divided by maybe 3 into 10 to the power 8, which is the speed of light, square it, don't square it, doesn't matter. This is going to be 0, because this is very close to 0. You're dividing it by a huge number, right? So that means this would be nothing but x minus vt divided by root over 1 minus 0. So that means this is just x minus vt. So this is x minus vt, and what is x minus vt? X minus vt is nothing but Galilean transformation, and that's why we say that at low velocity Lorentz transformation will tend to Galilean transformation, signifying that Galilean transformation is also not wrong, only not valid at higher velocity. So in our day-to-day life, Galilean transformation is valid. If we're talking about the speed very high, we're talking about Lorentz transformation. Is it true for time? The answer is yes, because in time Lorentz transformation is nothing but t prime is equal to t minus vx divided by c square divided by root over of 1 minus v square by c square. Here also we can consider that this velocity is very less than c, okay, then it will imply that t prime is equal to t minus, you see, v by c square. V is already very low and it is divided by c square. C square is very high because it will be 9 into 10 to the power 16 now, because it's a square term. So that means this will be almost very close to 0. So it is t minus 0 and divided by root over 1 minus again 0, same logic as above, this is t, which is nothing but the Galilean transformation. So that means if we are considering a velocity which is very low, and if you're putting it mathematically, the results are the same. Are they perfectly equal, Galilean transformation, the Lorentz transformation? The answer might not be yes, because if we are talking about using the Lorentz Galilean transformation and finding out the relation, you might get the time as, let's say, 1 hour. But if we are using Lorentz transformation, maybe with Galilean transformation we are getting this. I'll tell you or give you an example to solve. It will be very easy. But if we are basically measuring it in Lorentz transformation, the time might be, let's say, the velocity is 3000 meter per second. I'm just saying. Measure the time. If you consider the velocity to be 3000 meter per second, you can measure the time using Lorentz transformation, and you will find out that the time may be 1.0000000000000. I don't know how many zeros, maybe something like 2, 3, something like that. ऐसा कुछ आएगा. You can try, practice, do it. Lorentz transformation. So this is very close to this. So that means Lorentz transformation will tend to Galilean transformation at low velocity. 3000 meter per second is also very low. Okay, in general we might think that okay, it's very high, but it's very low. This is the speed of maybe fighter jet. Okay, so that is there, which leaves the speed of sound behind because it travels at the speed of sound. The speed of sound is much low compared to the speed of light. So we can do the calculation and see what is the time, and you will see this will be almost very close to 1 hour, because t is 1 hour. This is, you can take this as 1 hour, and you can take this as 3000 meter per second. Do the calculation, you'll see that this will be something like this. So there is no logic, so it's very low. So this is actually what is called the idea of Lorentz transformation. Okay.